All right, hello and welcome everyone to another Applied Flow Technology webinar. Thank you for taking the time out of your day to learn a little bit more about some fine modeling tips and tricks in AFT Impulse. Today's webinar, we're going to focus on transient check valve modeling. The wording I'm going with is check before you wreck, or check yourself before you wreck yourself. And how can you take a look at your model and your system in AFT Impulse before making any changes to your physical system, so you can predict and anticipate any issues before they're implemented. Before we go too far, my name is Nick Vastine. I'm a business applications engineer, and today I'm going to be walking you through a lot of our different check valve options, specifically in AFT Impulse. So today we're really going to start from our foundation and from our fundamentals. We're going to look at what a check valve is for, how they're constructed, some of their considerations that we have to make in what check valves are meant to do. We'll look at check valve slam and why check valve slam is an issue. If we can diagnose the cause of check valve slam, that'll inform how we can address those concerns, especially when we're making changes to an existing design or trying to select a check valve that'll avoid slam. To select a check valve that avoids slam, we have to think about how we can mitigate a slam event. Again, that comes back to the foundations of what causes that check valve slam to try to mitigate it and move forward with a improved design. We'll look at a check valve sizing procedure, so going through the steps and what considerations you have to make as you're picking your check valve or modeling it in AFT Impulse. And then finally, to kind of broaden it beyond the software, what other kind of considerations do you have to make when you're selecting a check valve or trying to model it in AFT Impulse? So we're really running the gamut today. We're starting from foundation fundamentals, what causes that check valve to slam, how to mitigate that slam event, part of which is due to the valve and the system and how those things are interacting. Looking at a sizing procedure, so bringing it to the real world application, and then again, finally, those other considerations you should make as you're selecting a check valve for your particular system. So starting off with the fundamentals, what is a check valve? Why is a check valve different from a normal valve? What's the real intention of this component? So check valves prevent a sustained reverse flow through a component. This is usually intended to protect a component where you only want flow going in one direction. The most common example of a component to protect is a pump, where the impeller and the motor and all the systems surrounding the pump is generally intended to flow in a forward direction. All of a sudden, if a pump trips and it no longer has that driving force, flow may want to reverse, spinning the impeller the opposite direction it was designed to spin, spinning the motor the opposite direction it was anticipated to, and potentially thrashing that component, causing damage. So check valves are great because it acts as an intermediary to prevent that reverse flow, or at least a sustained reverse flow instead of constantly churning that pump. So a few things can cause that flow reversal. We'll look at some of the causes a little later in the webinar, but the most common ones are a pump tripping and you're losing that driving force, or something like a surge event where a sudden high pressure downstream of a pump might cause flow to reverse. Check valves are a passive protection system, meaning they don't rely on things like operator intervention or a control system to operate. Instead, it's all driven on how flow reverses and how that change in direction of flow changes the state of that valve. As we'll see, there's a lot of different ways that you can design check valves, and they're going to create drastically different responses to a sudden flow reversal. A pretty common type of check valve is a swing check valve. This is a good demonstration of how a check valve works. If we look at the left, this will be the inlet of flow. So during normal operation, we have flow going from left to right. Part of that flow and pressure is going to cause this swing gate to swing up. That way it allows flow through in only one direction. If suddenly flow needs to reverse, such as if a pump over here upstream of the check valve trips, or if we had a surge event downstream and that causes flow to reverse, we're going to see this gate swing down and suddenly close. So that's what's going to create zero velocity. That's what's going to prevent that reverse flow from continuing and going through the pump and other components that we're trying to protect. Another application that we can see check valves in is, again, anytime we're trying to prevent reverse flow. parallel pumps might be a good example where if you have a collection of pumps in parallel and one of them trips, you're still going to see very high pressure downstream of the pump and relatively low pressure upstream of the pump. And so that'll cause reverse flow through this check valve. Obviously, you want to prevent that in that case as well. So these check valves aren't perfect because it's not going to prevent all reverse flow. If we could prevent all reverse flow, it wouldn't really be a major concern and we wouldn't have a cause for check valve slam. But as you can imagine, it's going to take time for this swing arm to swing down as flow is reversing. So there's going to be a certain amount of flow that does go in the reverse direction. And now all of a sudden, when this valve fully closes, we're bringing all of that flow to a stop. So in the same way, thinking about a traditional valve closure, where if you close it very rapidly and flow comes to an abrupt stop, that's going to cause a high pressure event. In this case, it's specific to how a check valve is constructed, and we call that high pressure response check valve slam. So what causes check valve slam? Let's break it down into a bit more fundamental concepts. Again, it's nice to look at the visual, but we can kind of isolate the different components of what causes a slam event to be worse than a comparable slam event. So again, check valves aren't perfect, so they're going to allow some amount of reverse flow before they close completely. Because there's a certain amount of reverse flow, once the check valve fully closes and that swing arm fully seats or a nozzle closes, that's going to cause a sudden rapid deceleration. So that deceleration, similar to Joukowsky equations and other pressure rises due to valve closures, that's going to cause a pressure spike, and that pressure spike is check valve slam. So there's two questions that we want to ask ourselves when we're considering check valve slam. One is how much reverse flow occurs. The more reverse flow that we see, the worse the slam event is going to be. The same way, closing a valve on a very fast moving stream is going to create a lot more pressure than a much slower moving stream. We also have to consider how quickly is the reverse flow stopped. So if we consider that valve approach again, if we gradually close a valve, it's going to create much less pressure, or it's going to be able to disperse that pressure that it creates much more gradually than suddenly slamming it closed. So if we look at the first part first, how much reverse flow occurs, that's largely going to be driven by the system itself. So the system has a certain amount of potential for reverse flow. If we use this diagram as an example, where we're pumping up a very large hill, if this pump trips all of a sudden, we're going to have significant reverse driving force for our flow. Let's say we were pumping up 500 feet in an extreme case. Now we have that 500 feet of head that wants to flow the opposite direction. The larger this elevation difference, the larger reverse flow potential will happen. An extreme comparison would be 500 feet of elevation gain compared to a pump pumping just against frictional losses. If it's just frictional losses, there may not be a lot of potential for reverse flow, if at all, whereas the more elevation you see, the more reverse flow can happen. Another case, again, one that we brought up earlier, is parallel pumps, where if you have a collection of pumps and they are all pumping at a large head, if one trips suddenly, it's still going to see that downstream high pressure from all the other pumps providing it, and now flow wants to reverse through that tripped pump. So it'll also want to flow through that check valve, and the more potential for reverse flow, the more likelihood there is for a check valve slam, because more reverse flow is going to be occurring. So this is largely driven by the system itself. So check valve slam isn't only a component issue. Like many water hammer issues or other transient issues, you have to look at the system in context and don't necessarily focus only on the component that you think is causing the problem, because your resolution may exist in a completely different part of the system. So how much reverse flow occurs, that's all driven by the system. How quickly is the reverse flow stopped? That's driven more by the component itself, but also by the system. So here we will look at things like valve characteristics. We saw how a swing check valve is constructed, but there's other types of check valves with different ways that it cuts off the flow. Some will slow that flow more effectively than others, or it might take less time for it to stop that flow. Another thing we have to consider is the rate of deceleration. This is more of a system context where the rate of deceleration describes how quickly you're going from positive flow to all of a sudden no flow, and this check valve needs to stop. So that can be driven largely by the system. A pump trip could inform that. So for example, if we had two pumps and one had much more inertia than a smaller pump, the pump with more inertia is going to take a lot longer to trip and gradually decay, meaning that it takes a lot longer for that slope or for the flow to approach zero. Compare that to a pump trip that trips really rapidly, and now it's a much more aggressive change in velocity, and the check valve has to react to that change much differently than how it would to a really slow deceleration. So this is just an introduction of the concepts. We'll take a look at these concepts in more depth, especially valve characteristics and this deceleration part. The system potential, that's a bit more self-explanatory, and that's generally going to be more restrictive within your own system. So that might be informed by other criteria that you have in your design. But again, let's think back to the big two pieces. One, how much reverse flow is occurring? The less that we can have, the better. And also, how quickly is that reverse flow stopped? Are there other things within the system that we can change to make it much more gradual to approach zero, which is going to lead to less check valve slam? Those are the two things that we're going to try to control in our system. So now that we know what check valve slam is, we understand what check valves are and the slam event, or the high pressure rise due to sudden stoppage of reverse flow. What are some approaches we can take to mitigate that slam event? In my book, I think there's really two options, and in reality, every solution is going to fall somewhere between these two options. The first option is to prevent any reverse flow by closing at exactly zero flow. This is what I would call an ideal valve closure, where that swing check valve doesn't let any flow through. It closes at exactly zero. What this does is it avoids any change in velocity, where the change in velocity and the deceleration of the fluid is what's causing that pressure to spike, but it isn't necessarily a realistic goal. So closing at exactly zero, if there was a perfect check valve and an ideal check valve, you could throw that into a lot of systems. There's a lot of check valves that get very close, but it's never going to close at exactly zero. You'll likely always see some amount or some degree of reverse velocity. An alternative is to gradually slow an allowable amount of reverse flow. Again, if we think back to a traditional valve closure and we get into that mindset, if instead of slamming the valve closed, we gradually close it over a much longer time, that'll mitigate a very high pressure rise. So that'll mitigate that check valve slam that we're trying to avoid. Again, this is going to largely depend on the system and the type of valve. The other criteria of how slow can you close that valve, or what's an allowable amount of reverse flow to go through your pump if that's the component that you're protecting, a lot of that's going to be informed by different design criteria. In reality, most check valves are going to fall somewhere between the two, where they have a certain amount of allowable reverse flow, and as we'll see in Impulse, it just slams it closed, so we have to account for that allowable velocity in terms of the pressure rise it creates. We'll look at a specific example that isolates that reverse velocity impact to see how that creates pressure and how that's really what we're trying to address with this check valve design and this check valve selection. Obviously, the best way to figure out how to mitigate a check valve slam event is to experiment in software. Hopefully, you've already experimented with AFT Impulse in your own systems. And it's good to recognize that in software, you're not limited to modeling just the check valve. You're not isolated to specifying things like the deceleration or what CV it operates at and what's the steady state flow rate. Instead, you're looking at a really system approach. So while there may be an issue with check valve slam, you don't necessarily have to address that issue at the check valve. If the check valve slam is caused by a pump trip, there's other ways that you can make a pump trip longer, so that way it isn't decelerating the fluid as aggressively, and that check valve doesn't have to suddenly look at super high flow and all of a sudden change to no flow and slam closed. There's other considerations you can make, like relief systems, or if you wanted to look at gradually slowing, you could look at something like a bypass, where it would close the check valve, but flow could continue in a different direction, essentially mitigating the rapid deceleration by redirecting it. But in essence, the most important part is considering other aspects of the system, not only looking at just the component. Sometimes as engineers, you can get too focused on a single piece, where changing something else to avoid the issue entirely may be a bit easier, and Impulse can certainly help you with that. So now let's take a look at an example. Let's see some check valve slam in an actual system. So here we can take a look at a graph where we're looking at that pump trip from that initial system. Here we'll see how the velocity gradually decreases. This is the pump tripping. Then we can see how at 0 meters per second of reverse velocity, 1 meter per second of reverse velocity, and 2.5 meters per second of reverse velocity, all of a sudden that check valve is closing, and that causes a corresponding pressure rise or a check valve slam. So we'll take a look at how I made this graph in Impulse and some ways that you would specify it and sort of my approach to doing this type of analysis. One thing to note is that check valve closures in Impulse are always going to be instantaneous. So here we can see as soon as it reaches that reverse velocity, it's going to go to immediately closed. So a lot of what we're doing here is all dependent on that reverse velocity. That's why it's so important to get that number as close to accurate as possible. So that way we're accounting for that slam and the highest potential pressure rise that our system would see. So if we think about the Joukowsky pressure rise, again, we can look as our change in pressure is equal to our density of the fluid, the wave speed, or how quickly a pressure signal transmits through a piping system, and then the change in velocity seen by that fluid stream. You can think of it as an energy balance where you have a particular amount of momentum, and when that momentum suddenly disappears, like when your check valve closes, that energy has to go somewhere, usually in the form of a rise in pressure. So it's important to see that this is directly correlated. The faster this is going to go, the higher pressure rise you're going to see. So let's take a look in the software and let's see some of the concepts that we've talked about in practice. So here we're running an example model where it's just modeling a pump trip and we are adding a check valve element into it. In the pump, there's an easy way to specify a check valve. So we have a couple options to add a check valve in Impulse. We have a combined check valve and pump, where if we check this, we can specify that forward velocity to close. Again, this is what's going to inform that check valve pressure rise once it reaches that point during the trip. And we can also look at the delta head to reopen or the delta pressure to reopen. So if you have a check valve that might chatter, if you trip the pump and then restart it and you need that check valve to open, this is what you would use to define that. So this models everything internal to the pump. We also have check valve options from a junction standpoint, and we'll look at some of the additional flexibility you get with that junction. But for now, we're going to focus on the concepts and we're going to focus on that allowable reverse velocity. So here I've created a scenario tree. It's always good to have a steady state run to understand what assumptions are going into your system or what's your starting point. And here I have a scenario where we're going to compare all of our allowable reverse flows. Here we have a scenario with no check valve. So this is the same as our base scenario. We don't have a check valve specified. Here we have our essentially ideal check valve closure, where we are closing the valve at exactly 0 meters per second. Again, this may not be the most realistic representation, but it does show other pressure rise effects that wouldn't be caused by a check valve slam. So if you're adding a check valve into your system and you just want it to close at 0, understand that that may not be the best representation of what will happen in your physical system when the check valve actually closes. So we'll look at 0 meters per second. We can also look at 1 meters per second. So here, an interesting caveat to note is that we're specifying the forward velocity to close. So if we made this a positive 1, that means that flow will be in the forward direction going 1 meter per second, and then this check valve will close and go to 0. You can think of it if the fluid doesn't have enough momentum at 1 meters per second to overcome this swing check valve in this small diagram, then it should close earlier than the ideal case at 0. If we want to allow some reverse flow, we're going to make it a -1, indicating that it's now a reverse velocity. Again, we're going to leave delta head to reopen at 0. Just for isolating different pieces, we're not going to look at the chattering of the check valve necessarily in this case. We can do the same thing with 2.5. Again, specifying -2.5 meters per second, where here we're going to see much more significant slam as we saw in that graph originally. Here we have all of our child scenarios. If we wanted to make changes, we could always make changes in the parent. If we wanted to test the impact of the upper reservoir level, again, seeing, what's the potential for reverse flow, if this were 0 or if it were 100 meters. And then what I would do is with all these child scenarios, I would start a batch run. And here you can run all of those scenarios in sequence instead of kind of babysitting Impulse and waiting for one to finish before starting the next. So in this case, we already have our output. So we're just going to go into the graphing and looking at the analysis of the system. So if we look at our workspace, we'll keep this on the left to keep us with a good picture in mind. And now we can move to the graph results tab. So I like to focus on graph results in transient analysis because it's much easier to picture the system over time and the density of information that you get is a lot higher. So in this case, we want to look at downstream of the check valve. Because we don't have a check valve junction, we're going to be looking at the inlet of pipe 2. So again, if we go to graph results, we can look at pipe inlet. And here we want to look at the static pressure, and then we'll also look at the velocity. So by clicking add, we can stack them on top of each other. And here we can see that reaction. So here, our time scale is a little long. So we'll zoom in to the first 10 seconds. Here we can see the pump tripping, so we can see that the velocity gradually decreases until it gets to -1 meters per second, and there it closes very suddenly, creating this pressure rise. Again, this is that Joukowsky pressure rise. Imagine if you're slamming the valve closed, what sort of pressure rise are you going to see? That's in essence what we're doing with this check valve, but we're basing it off of this reverse velocity as a kind of trigger to initiate that behavior. So another way that we can visualize this is with a profile graph, so we can see how that pressure wave might transmit through P2. And another step would be taking a look at the resultant forces. But we won't go to that depth. Of course, we can have our own webinar on forces, and we have in the past. So here we're going to keep the focus on check valves alone. So if we instead look at a profile graph, let's look at the full profile. So we'll start here, show this length of pipe, add the pump, and then this length of pipe. We'll look at the static pressure and then this velocity as well. And let's do this. Let's do it in a new tab. That way we can look at both our previous graph and our new graph as well. What I like to do is animate our output. You can do that from the analysis, transient control, pipe station output and set this to all stations. That way we can look at the intermediate points between all of our different pipe segments. So we're not restricted to the inlet and the outlet. We'll get rid of the maximum and minimum. And here we can see what our system looks like along the length of pipe. So we see our lower reservoir, we see the pressure added by the pump, and then we see how that pressure decreases as it rises and it sees frictional losses. Velocity is fixed because we have the same size of pipe, so mass continuity is maintained, and then the velocity is going to be consistent through the whole pipe. Now, if we start our animation, we'll look at how that pump trips and how that'll impact the pressure, and then we'll see when that check valve closes how a pressure spike should occur, and that pressure spike is that check valve slam that we're going to be trying to capture and hopefully try to mitigate. So if we hit play, we can see how the pump trips very quickly. Let's see if we can slow it down a little bit. So here we see the pump tripping. Here we still see there's some forward flow. Static pressure doesn't tell the whole story because we're also pumping up a hill. Now we are at 0 velocity. So in our ideal case, it would have closed already. And now at -1 velocity, we see that huge pressure rise. So let's go through that time step by time step. Again, no pressure rise, check valve isn't closed yet, check valve suddenly closes. Here's that check valve slam that we would have to be concerned about. So we can see the water hammer sequence, where that's going to be its own webinar again, of course, where that's just diving into that topic is a lot. But we see that high pressure wave that'll go down the line, it'll reflect, and then we see that reflection bounce back and forth as well. So something new to Impulse 8 is the ability to compare multiple scenarios at the same time using these graphs. It's easy as creating your profile graph. Again, this is great if we're isolating one variable, in our case, the reverse velocity for the check valve. And here we can add different scenarios as well. So if we click select scenarios, here, similar to that batch run, we can choose which scenarios we want to see. And if we hit OK, we can hit generate. And now we see all 4 of those situations at the same time. So if we go and compare these, again, they all share the same trip event, so they all start at the same reference point. That's a good check as well. Our first reaction point is now going to be our ideal check valve closure at 0 velocity. And then we'll see how that pressure rise compares to the other pressure rises created by the other check valve events. So here at 0, we don't see that extreme pressure rise like we did in the 1 meter per second, which we'll see here in a moment. Where boom, that's our check valve slamming closed, creating this pressure rise. And now if we let even more reverse flow go through and suddenly slam it closed, we should see an even higher pressure rise, which we do. So we see, nearly double, which makes sense because we're doubling the amount of velocity that we are suddenly bringing to a stop with this check valve. So this is great to compare multiple scenarios. Again, if you're isolating variables and you want to do analysis and comparison between all of them, this is a great tool because it's building on that graphing foundation that a lot of Impulse users, I'm sure, are much more familiar with than relying on output or visual report or anything like that. We can do the same thing with this graph. So here we look at time in the x-axis and then our different variables in the y-axis, but we're localized to a position in the pipe. Again, in our graph, we just click multiple scenarios. We can select our different scenarios, add our different pieces, generate it again. And here we can see, let's turn off the legends, that 0 velocity closure, where there is a slight pressure rise, that actually comes from this reverse flow. It still has momentum, so it creates some pressure at this point. And then we can see our 2 slam events. So we see where the -1 velocity slams, that causes this pressure increase, and the -2.5 velocity slam, which causes this much more significant pressure increase. We can also combine these graphs. So now we're getting even crazier. We looked at multi-scenario profile animations, and we looked at multi-scenario transient pipe graphs. If we save those things as graph items, let's consolidate this real quick. So here we have that same graph that we just looked at, and we have that same animation, but I just saved them to this graph list manager by right-click, add graph to list. If we load them into this folder, what we can do is right-click, load folder tools, and click same tab. And now we can see how the profile and this graph relate over time. So even as a user of the software for more than 2 years now, I get to do these webinars and support all of our customers. I got to learn this just the other week, and I'm happy that I get to now share it with you guys. So if we hit play on our animation, again, we see that pressure decrease. We can see how it tracks along in this graph. Again, that gradual trip, we still see that positive velocity as it gradually decreases. And then we'll see how those trip events or how the check valve slam events are going to create that pressure wave, and that'll fan out through the system. So we're coming up on our first closure, this ideal closure, where you see that gradual increase in pressure. It's not a kind of spike event. There we see our significant increase at -1 meters per second. And then if we wait for our 2.5 meter per second closure, there we can see how that high pressure is transmitted through the system. So you can imagine with a simple system like this, where we're only looking at a few pipes, this analysis makes it very clear. But again, if you are balancing what's the interaction of these different components, or how are pressure waves distributing through your refinery or your cooling water system, visualizing it with graphs like this is going to make the analysis much more intuitive, instead of just looking for, well, what's the max pressure that I'm going to see. This really reveals what the cause of the issue is, rather than just the result of the issue. So I thought this was pretty neat. Hopefully you think it's pretty neat too. If you haven't seen this before, it blew my mind. So hopefully I got to blow your mind today with this graphing feature. So that's really what I wanted to show with this reverse velocity component. Again, the more reverse velocity that you're going to see through your check valve that you're suddenly closing, the worse pressure response you're going to see. So the question becomes, how do you either determine what is allowable for your reverse velocity in terms of what your pipes can withstand in terms of a pressure rise, or how do you get as close to that ideal check valve closure at 0 meters per second as possible? And that we have to get back into the concepts and think more about how these check valves are operating, and some other thought process that has gone into check valves as a science, right? So we've looked at the system components. If there's a higher elevation gain, if there's more driving force for reverse flow, the harder it's going to be for your check valve, as well as the faster you decelerate. So the faster that you go from 100 meters per second of flow, I hope you're not flowing that fast in your pipes, but the faster you go from that high velocity to 0, the harder it is for that check valve to react. And that's going to largely depend on the valve itself as well. So here we have a few different ways that check valves are designed. Here's that swing check valve that we started with, where flow goes left to right, pushes it up. Then when reverse flow happens, the swing arm has to travel all this way, allowing for pretty significant reverse flow through it. Again, reverse flow is the enemy of check valve slam. So anything that we can do to reduce the amount of reverse flow going through that check valve, the better we're going to mitigate that check valve slam event. In the middle, we have a nozzle check valve, which flows right to left, where again, it's going to create a bit higher losses to begin with, and it should close much more rapidly. You can see the amount of distance that this component has to travel to fully seat off and close is a lot smaller than the amount that the swing arm has to travel. So we would expect less check valve slam out of something like a nozzle check valve than we would out of a swing check valve. Here we have another example with a ball check valve, where it has a spring that is compressing. And again, this ball is moving to either seat or unseat depending on the direction of flow. So check valves in general, it's important to consider what type of check valve you're looking at, because that's also going to drastically change your response, in theory at least. To isolate these effects, this is called valve characteristics. You might have heard of valve characteristics in other valve closure contexts, where closing something like a gate valve compared to a ball valve compared to a globe valve, those are going to create drastically different responses because they're going to change flow at drastically different rates. So you're going to see something kind of similar here, but from an impulse modeling standpoint, it's largely deciding what is that reverse velocity that that check valve is going to close at. So the question then becomes, how do we determine what that reverse velocity is? This leads us to the process of how to pick a check valve to avoid slam. So it comes back to the 3 factors that we're trying to consider. First is, how quickly are conditions changing? How does that check valve need to react if flow slows really gradually compared to if flow comes to a halt instantly? We can look at how the valve itself reacts. So our comparison of swing check valves to ball check valves to nozzle check valves, the distance they have to travel and how they're constructed, that's going to impact how it reacts to a particular event. Finally, depending on those 2 factors, how much reverse flow is going to result. And based on that reverse flow, what kind of pressure rise is going to be caused by that check valve coming to a close. Some big names in the kind of hydraulic world, Thorley, I'm sure you might have heard of if you're in this realm, Ballin as well. They did experimentation where they compared different valves and how they reacted to different decelerations and what was the maximum reverse velocity that they found. So here we can see something like a nozzle valve where it has very slow or very little movement that it requires to cut off flow. That's going to react very differently to something like a swing check valve. So we'll look at what this graph means. We'll break it down into its components. The first component is how quickly conditions are changing, or that deceleration piece. We can think of deceleration as the change in velocity that we're seeing and the time it takes to go from that non-zero velocity to zero. So on the x-axis, we have deceleration. The more aggressive that we're changing flow, the harder it's going to be for the check valve to react quickly, right? So if we look at our swing check valve, that's the most typical example, where rapid deceleration, it's probably going to allow more reverse velocity. So here we can see the more deceleration, the more to the right we are, the more reverse velocity we see, compared to at lower decelerations, the lower reverse velocity we see. So this upward trend is consistent for all different valves, but it's going to depend on the type of valve itself. So that brings us to part 2, how the valve itself reacts, or these valve characteristic curves. So again, if we're comparing a swing check valve in construction to a nozzle check valve, because those are constructed completely differently, they're going to react completely differently to the same amount of deceleration. So the higher you go, the more max reverse velocity you see. For a particular deceleration, the more slam you're going to see. Again, reverse velocity is the enemy of check valve slam, and the lower reverse velocity we can have, the better. That brings us to our third factor, how much reverse flow results. That's our maximum reverse velocity. Again, that's important to consider based on this Joukowsky equation. So the more velocity we see here, the more pressure that we're going to see once we have to bring that flow to a stop. So something like a nozzle valve, we can see that it has very low maximum reverse velocity across a lot of different decelerations. This would be sort of the best kind of check valve. Whereas a swing check valve, it might be okay at really low decelerations, but the more and more you're thrashing the fluid around and the more quickly you're changing how that fluid is flowing, the less it's going to effectively prevent a slam event. The more reverse flow it's going to allow, and then all of a sudden when that valve closes, that's going to cause a slam event. So we can think about this graph, again, largely in terms of reverse velocity, where at really low reverse velocities, we're essentially seeing no slam. At higher reverse velocities, we see some mild slam, and then at higher, we see severe slam. So in some cases, something like a nozzle check valve is going to never see slam. But like anything in engineering, there's always going to be trade-offs. A nozzle check valve is probably more expensive to maintain or more expensive upfront than something simple like a swing check valve. So let's do an example. Let's make it a bit more concrete in terms of how you would use this graph to your advantage and how you can use this graph in Impulse as well to select the check valve. So a lot of these characteristic curves are specified in Impulse. We'll take a look at an example of that a little bit later. But first, we'll take a look at an example. So let's say, for the sake of example, our steady state velocity through a check valve is 5 meters per second. So that's our starting velocity. Let's say we have a pump trip that goes over 1 second, so a very rapid pump trip where it's going from 5 meters per second to 0 meters per second in 1 second. In our case, we want a no slam check valve event. That means that we're limited to looking below this line for our options. And that's our criteria for design. So the first step is determine what that deceleration is. Here we can see it's 5 meters per second squared. We can add a line here, which means that anything above here, that's going to be even more protected than below here. You wouldn't want to operate on this side and hope that it works up here, because the more deceleration, again, the more reverse velocity you're going to see, which causes an even higher check valve slam. So that's the deceleration. There's some other nuance that we can get into in impulse specifications to determine this number, but that's the most simple way to think about it. What's your starting velocity and how long does it take to get to 0 velocity? Depending on that deceleration, we can look at the different types of check valves that fit below our maximum reverse velocity. So here we can see that we have quite a few options. Again, this is where all the other engineering decisions start to come in of how reliable is it, how much does it cost up front, what does it cost to maintain, but you have a wide set of options to consider, and you've also ruled out quite a few options to look at, which is good. So to see this in practice, why is it important to consider what type of check valve that you're using and how can the type of check valve avoid check valve slam? We have a case study. So this came from Aquatech in Barcelona, Spain. They are looking at a water system where they're supplying their city with water, and they wanted to look at, one, the impact of check valve closures on surge pressures, and then they also wanted to look at the field data they can collect with that and compare that to impulse results. In this case, they were going to compare swing and nozzle check valves because that's how they were addressing the issue that they were seeing. So they used AFT Impulse, they modeled their water delivery system, they looked at the highest neighborhood. So in this case, it was pumping up 500 feet to a collection of houses, I guess. And again, that high pumping, that creates a lot of potential for reverse flow. So it makes sense they want to address check valve slam in this situation. They looked at all sorts of different scenarios. And as we'll see when we look at their model, their imported GIS information sped up their model construction. What they found is that their nozzle check valve reduced their max pressure rise by 63%, so a good surge pressure mitigation. And they also found that their field data that they measured matched the impulse predictions, which is always reassuring as an engineer. You're only as good as your tools and you're only as good as the assumptions going into your model. So if we take a look at their system, this is what they imported from GIS, where they have their pumping station all the way over here. Again, they were pumping up 500 feet, so there's a lot of potential for reverse flow, and they were looking at pumps with swing and nozzle check valves. Then all the way over here, 500 feet later, this was the highest neighborhood they were exploring. Here's a picture of the pumping station. So it's always good to remember that you have to get outside of the computer and think what's the real world implications of your decisions. And here we can take a look at the results. So here we have the swing check valve on top. We see a peak pressure around 220 meters of pressure head. And here we see that nozzle check valve. So the same transient event causing both issues, but here we see drastically different pressure responses, again, due to those valve characteristics. So one is going to be handling that deceleration much better than a different type of valve. We have a quote from the engineer: "In the light of the results of this study, AFT Impulse has proven to be a robust and highly reliable software to perform surge analyses." Funnily enough, this case study and all of our other case studies are submitted by users every year. This year, we have already started our Platinum Pipe Awards. So if you have a project that you're excited about and you're looking to score some street credit or some money for yourself and some money for your company, feel free to submit a project and we'd be happy to take a look and see how you're using the software. Note that if you do submit, feel free to reference this webinar and reference me, Nick, as your reference, because we do have some internal incentives for promoting this source of case studies. And also I get to review them. I get to write up a lot of these case studies, and I love seeing how you guys, the users, are using the software. Makes it a lot more interesting than, writing emails or coming up with arbitrary examples. So you have until October 31st. If you have any questions, you can always email me directly or email our webinars at aft.com. So plug over, let's take a look at how we can model different check valve options in AFT Impulse. So again, bringing it back to the software, how do we consider those different characteristic curves and the deceleration in Impulse? So the first option is the option we already looked at. This is the most simple way to model a check valve in Impulse. That's the combined check valve and pump. This is when the check valve and the pump are one harmonious thing. This is useful to avoid sectioning concerns. So if you have a check valve that in reality is only 1 foot away from your pump, but you're modeling it on a pipeline where there's thousands and thousands of feet, it would be useful to avoid the concerns of sectioning with the small sections added between a check valve and a pump and that long pipeline that follows. Again, it's useful to avoid sectioning concerns, but it's also only as good as your input. So it's only as good as your guess at that reverse velocity, or that allowable reverse velocity. You can also use the check valve junction, which introduces a bit more complexity and a few other ideas and concepts that you can use. The first option is user specified. This is doing the same thing as the combined check valve and pump, but now it's isolated as a junction. Here you're specifying that reverse velocity check, and then it also has the option to reopen. Here you can estimate from fluid deceleration without the opportunity to reopen, so you wouldn't be able to model a chattering check valve or a pump restart following a trip, but you can use things like the valve characteristics. So all those characteristic curves, those are all built into Impulse already for you to pull from, and that will determine that forward velocity to close for you based on the deceleration. So especially if you're looking at a range of transient events that can cause a reverse flow, it would be good to see how the check valve reacts to that range of circumstances instead of just setting one forward velocity and assuming that it'll be the same across all those decelerations. The final option is a force balance, where it models the actual internals of a swing check valve and a nozzle check valve, balancing things like torque on a swing arm and the forces of a spring on a nozzle. So as you can see, there's quite a few different options. I've organized them kind of increasing in complexity. So what I would do as a user is start with a kind of general forward velocity to close, see what sort of response you get from there, and then increase in complexity if that is a significant cause of concern in your transient analysis. So let's take a look at what this looks like in the software. Here again, we have another scenario where we'll organize this again, where we've added this check valve. Here we have a user specified, where again, we're just specifying this forward velocity to close the valve, and then this delta pressure or head to reopen. So just like what we see in the combined check valve and pump, where it's that forward velocity to close, delta head to reopen. Easy enough. Where we get more complex and a bit more interesting is this fluid deceleration. Again, it won't reopen, so if your pump restarts or if you have chattering check valve concerns, this would not be the best option in those cases. Here we have the performance data. We have dimensional data. If we go to none, we can see that same graph that we just talked about with deceleration on the x-axis and that maximum reverse velocity. So depending on which check valve you select, here we'll look at a swing check valve. Here you can see how that maximum reverse velocity is going to increase really significantly depending on that deceleration. Here we have an option to do dimensional or non-dimensional. Dimensional, this is based on actual test data run by the authors of these textbooks and the sources that we got this information from. What that means is that this is limited in scope to the test or to the valves that they actually tested. In this case, they were looking at 800 millimeter swing check valves and 500 millimeter nozzle check valves. If you look at nozzles, and then 8-inch valves for all the others. So if you're trying to use this dimensional data for a 16-inch valve or a 2-inch valve, you're going to lose some resolution here. Instead, what you should do is use this non-dimensional. So here it's isolating the shape of the curves, and now you can determine, depending on what you know about your system and what you would know about your check valve, how can you scale these different shapes to something that'll be dimensional, something that Impulse can use. So the additional specification is this minimum velocity required. In our case, again, it's a pretty generic example. We're just going to rely on this dimensional for our example. So here we would define that swing check valve. It would highlight it, and then depending on that deceleration that Impulse would calculate, it would determine that allowable reverse velocity and then close the check valve at that point. You can do the same thing with a nozzle check valve, where here we have a strong nozzle and we would expect much less pressure rise than the swing. And as before, I've created a graph where we can look at comparing the two types. So here we see that reverse or that velocity decrease. And then again, we can see how this reverse velocity, that's going to be dependent on the deceleration. So if you wanted to experiment with something like adding a flywheel and seeing how your current check valve would react, it would account for that change in deceleration automatically to change what this maximum reverse velocity is. But again, in all cases, it's going to close instantaneously, and you'll see that pressure rise. So that isolates those effects. I don't think that this is as cool of a graph as that case study, but again, it drives that concept home where accounting for those valve characteristics are going to impact your results as well. So the final option before we get out of here, also we can look at kind of the math behind it. So if you wanted to dive in a bit more and really understand the fundamentals of how it's doing that calculation, you can look at how it's determining that deceleration, essentially looking at that steady velocity and at what point it goes to zero, and then the time it takes to do that, and how it accounts for the size of the valve based on that velocity that you're specifying. We can also take a look at the force balance. So as you can see, this is a pretty short section. There's only two equations. The force balance, we have all of these torque pieces and the angular momentum and all of this math. And so now let's see what all of this math goes into. Here we'll create another scenario where we're going to look at the force balance, our final option in the check valve junction. In the force balance, you can enter force balance data. And here we are going to be modeling the actual interaction of the fluid and the different component that's floating in the fluid. So we have the swing check valve. We also have a nozzle or plug valve. So if you are a check valve manufacturer and you want to see how it'll react based on these different variables, or if you have a component where you know all of this information, but you lost the data sheet for that component, this could be a good way to approximate that check valve closure. So here it accounts for other things like the distance to the center of the swing arm, the area, the weight of it to account for buoyant force, what's the overall inertia since it is a momentum and a torque balance, and then also what CV will react at the different various open percentages. You can also include things like a spring, or if your pump or if your check valve is vertical, how would that impact how this operates? Now you're going to have gravity helping you a lot more. So we won't go into the specifics of specifying this. This is a bit more fine-tuned if you have been looking for this and you're like, man, I only have this information and I have no way to define it. Now maybe this is a way that you can take a look and experiment. So that's the force balance. Generally, I would recommend, again, starting with user specified, maybe look at an ideal valve closure and see if the check valve even closes, and then maybe start with a conservative estimate. And then as you get more complex, you can look at the deceleration and start considering these other impacts like different decelerations for different events or different check valves that you have to select from. All right, so that brings us through all of our different options, our user specified, fluid deceleration, and our force balance. And that's really the modeling aspects of check valve selection. So there's some other considerations that as an engineer, I'm sure you'll have to make before you can justify any decision. One is going to be the initial capital cost based on valve type, size, the associated piping and the supports, the different recurring costs associated with a component. So what are the losses that check valve will create at full open? The more losses that it creates, the more energy that you're losing when you're adding it from a pump and it's immediately lost through a check valve. You also have to consider maintenance costs. So what complexity of component is going to create more maintenance for you and your operators. Fluid type is another consideration. So you may not want to pump something like a slurry of sand through a nozzle check valve, but it may be okay to go through a swing check valve. And then finally, you want to look at the potential for check valve chatter. So making sure that you have enough pressure in normal steady state operation to fully open that check valve and minimize the losses that it's seeing. And during a transient event, will it oscillate between an open and closed state? All right, so that was a lot to take in, I'm sure, but hopefully we've all learned something today. Let's review what we've gone over so far. So we started with our foundations. What is a check valve and what is the point of a check valve? Again, it's to protect equipment from sustained reverse flow. If improperly designed, some of that reverse flow can go through, and when that check valve ultimately closes, that can cause a secondary transient issue. We call that pressure spike check valve slam. That slam is due to the rapid deceleration of reverse flowing fluid. The closer you can get to 0 reverse flow fluid, the better your check valve closure is going to be and the less slam that you're going to experience. There's a lot of considerations with the construction of the check valve and the different types of check valves and how that's going to respond to different reverse flow. It also depends a lot on the deceleration aspect. So how quickly is that flow coming to a stop? And we see that in all cases as that deceleration increases, there's much more likelihood for reverse flow and therefore much higher likelihood of check valve slam. So that's the summary. I want to thank everyone for attending, especially if you've made it through the full hour. Hopefully you found some tips and tricks that you can use in your own model. Again, take the concept that you learned here and expand them out, apply them to your larger system outside of our more conceptual examples. If you have any other questions or comments on the content that we've had today, you can send any inquiries to webinars@AFT, and I'll do my best to personally respond to them. As we go into the back half of the year, we're going to start looking at webinar topics for the next year. So if you have any ideas or if you have a specific industry or a project, we would love to hear about it. So you can also submit topics to webinars@aft.com. Again, I want to thank everyone for attending. Thank you for your hour, and hopefully it helps you in your modeling journey going forward. Thanks again, and we hope to see you in future AFT webinars as well.